Electric field. In this module you will learn to derive the expression for electric fields for a uniformly charged infinitely long, thin, straight wire by applying Gauss's law. Consider an infinitely long, uniformly charged wire. To find electric field due to this wire, you would perform vector addition of each component of electric field, making the entire process too complicated. To avoid this complexity, you can instead apply the Gauss's law, which enables us to find the electric field by a simple method. To understand this method to find the electric field, consider a thin, straight, infinitely long wire with uniform linear charge density, and then consider a cylindrical Gaussian surface, which is an imaginary symmetrical surface with wire as the axis of symmetry. To explore the symmetry of the closed cylindrical surface, consider any point on Y. Then take the radial vector r from this point to any point P and rotate vector r. As all the points at the end of the arrow are equidistant, they will have the same value of electric field. Next, consider two small elements A and B on the wire, equidistant from the point P. The electric field due to both the elements will be equal in magnitude. Both the electric fields are resolved along the parallel and perpendicular axis. The field along the perpendicular component cancels as it is equal and opposite, whereas the parallel component adds up, giving a resultant electric field in the radial direction. Thus, for any such pair, the field at any point P is radial, forming a cylindrical symmetry. Based on the fact that the field is radial leads to cylindrical symmetry, the flux, which is the dot product of electric field, and the surface area is calculated across the surfaces S1, S2, and S3 of the cylindrical Gaussian surface. The curved surface S1 is parallel to the electric field E. Surfaces S2 and S3 are perpendicular to the E. Hence, flux will be zero at S2 and S3. As the flux across the surfaces S2 and S3 is zero, the total flux is only due to field lines passing through S1. Based on the Gauss's law, flux is total charge upon epsilon zero. The total charge in a closed cylinder of length L is lambda L, where lambda is linear charge density. Then by using Gauss's law, the electric field E is equal to 1 upon 4 pi epsilon 0 2 lambda upon r. The vector form of electric field E at a point is given as vector E equals to lambda upon 2 pi epsilon 0 r along unit vector n in the radial direction. Unit vector n is in a plane, normal to the wire passing through the given point. Electric field is directed outward if the charge is positive and inward if the charge is negative. In this module you have learned the electric field has the same magnitude at every point of the cylinder and is directed outward for positively charged wire. The electric flux is equal to the electric field times the area of the cylinder. The electric field E for a uniformly charged finitely long thin straight wire is equal to 1 upon 4 pi epsilon 0 2 lambda upon r.